Hey guys, I got a request for some IV gravity drip problems. So I'm going to go through some. I have another video, I'll open it up for you. But I thought I would do some with dimensional analysis first, and then I'll show you the division factor again. Anyway, IV gravity problems kind of bug everyone because in clinical you're used to seeing pumps. And you don't get to do them a lot, so you never get real comfortable or familiar with them. But they are a rite of passage in nursing school. We do expect you to graduate knowing them, so I'm going to make this video, and hopefully it'll be a good refresher from 135. So in dimensional analysis, we always start where we hope to finish. And what we want is how many drops are going to come through that chamber every minute, because that's what we can count to make sure our rate's correct. And you know that you're going to line everything up so that whatever's in your answer is aligned. Your drops are on top, your minutes are on the bottom. So this problem looks a little complicated. We have a tubing drop factor, and all that means is that the size of the drops equals 15 drops to 1 ml. So let's go ahead and put that where it belongs. Drops on top, an ml on the bottom. And then we see that we have 1,000 mLs over 10 hours. So, there we go. And our mLs are going to cancel, which is what we want. We need to convert those hours to minutes, though. So let's do 1 hour equals 60 minutes. Now, if we set this up correctly, everything but our drops per minute will cancel out. So hours cancels, mLs cancels. We don't need them, they're gone. What we're left with is drops per minute, which is what we have in our answer. Okay, so now that we know that we set it up correctly, we just multiply across, and what you end up with is 15,000. Sorry for the sloppy handwriting. My stylus is really not that correct. And then 60 times 10 is 600, right? So multiply across, and then you can get out your calculator, or you can do it in your head or on paper, however you want to do it. What you're going to end up with is 25 drops per minute. And you're going to have to stand there with your watch and adjust that roller clamp until you get to 25 per minute. And the second the patient moves, the rate's going to change because it's gravity. But that is how you do the math. Okay, I'm going to do some more problems. Okay, so our second problem is going to be D5LR, dextrose 5% in lactated ringers. It's supposed to go in at a rate of 125 mLs per hour. And now our drop factor is 20 drops per ml, and you're going to notice that the drop factor is always going to be some factor of 60. Everything is going to be divisible into 60. So you have 10 drop sets, 15 drop sets, 20 drop sets, and 60. Just tuck that away in the back of your head, and we'll work it out with the division factor in a little bit. But first, dimensional analysis, because, you know, it's our thing. So we want drops a minute per, again, that's always what you're going to want in your answer with an IV gravity rate, because it's the only way that you're knowing that your solution's going in at the right rate. So let's get our drops on top, 20 drops per ml. And now in the problem we have mLs per hour, which makes it tons easier. So 1 ml, or 125 mLs per hour. And we know that 1 hour is 60 minutes, so our minutes are now on the bottom. Let's cancel our stuff out. Hours goes away, mLs goes away, left with drops per minute. We can multiply across. And when we do that math, we end up with 2,500 over 60. When we do that division, we have 41.66, the repeating decimal. You know that your eyeball cannot count 2/3 of a drop. It's just not possible, it's not precise. So we round to the nearest whole number, which in this case is 42, okay? Now, I know this is basic second grade math, but I'm going to go over it anyway because some people just don't think about it. They see the 41, or they, you know, they forget about rounding rules. If you have, let's get rid of some of this junk. Sorry, just erasing. If your number is something 0.1 to something 0.4, you're going to round down. So let's say if we have 41.2, we round down to 41. If your number is 41.5 to 41.9, we round up, and you end up with 42. I know it's basic math, but just things like this trip people up all the time, and it's silly. Honestly speaking, is there such a great big difference between 41 drops per minute and 42 in the real world? No, not really, and if you're that precise, you should be on a pump. But, you know, this is the world of nursing school, and you have to adapt. So that's the answer. Okay, so our next problem we're going to go through really fast. We have half normal saline at 175 milliliters per hour with a drop factor 20 drops per ml. Let's go ahead and set it up, dimensional analysis. Do it on the right, do it on the left, doesn't matter. But start where you hope to finish. Okay, drops per minute, that's what we want. So we put our drops on top. 175 mLs per hour, mLs is going to cancel. An hour takes 60 minutes, so our minutes are on the bottom. Hours cancel, mLs cancel. So excited we have drops per minute at the end. You're going to end up with 3,500 over 60. And that calculates to 58.33. We know we're not going to count a third of a drop because we left our bionic eye at home. So 58. Make sure you specify that you are counting drops per minute. The end. Okay, let's do one more. So we have lactated ringers ordered at 100 mLs per hour. The drop factor is 15 drops per ml. This really is not a different problem from the very first one we did. I'm just calculating it at mLs per hour instead of 1,000 over 10 hours. And then I'm going to show you division factor because it's going to make more sense. So, well, not to be so repetitive, but drops per minute over here. Put our drops on top. Sorry for the sloppy mess. 15 per ml, and we have 100 mLs. We want that to cancel, so we'll put that on top. 1 hour, and we know 1 hour is 60 minutes, and we have our minutes on the bottom. So let's go ahead and cancel. Hours cancels, mLs cancels. It's always kind of the same. It should be. So what you end up with is 1,500 over 60. You do that math, and you end up with 25 drops per minute. And now, for my next slide, I'm going to show you the division factor. And if it makes sense, it makes sense, and it's real quick and easy. And if it doesn't make sense, forget about it. Put it all in dimensional analysis, and you won't screw it up. Okay, so I just wanted to talk a little bit about the division factor. If this is confusing, don't use it. But it really is a pretty quick and easy way once you understand it. It's just based on the principle that all of your drop factors in your tubing are factors of 60. So whether it's a micro drip that's 60, 20, 10, or 15, it's going to go into 60 evenly. When you set that up in dimensional analysis and you have your 60 minutes on the bottom instead of your hour, you'll see how that sort of cancels itself out, and you end up with this division factor. I'll illustrate it in a second, but anyway. So you're never going to have a tubing set that is 11 drops per ml. You're never going to see 27 drops per ml. It's always going to be these nice even factors. And what you do with that is you divide your hourly rate by whatever number that drop factor multiplies to get 60. Okay? So if you have a drop factor of 60, that's your micro drip tubing. And you know it's micro drip tubing because you'll open the package and there'll be a little tiny pin inside the chamber, and that's to deliver really tiny little drops, because 60 drops equals 1 ml. Think about the size of an ml and think about how little these drops have to be. That's micro drip tubing. Now, to get your drops per minute from that, you need to know your hourly rate, and you don't really have to do anything to it, because 60 goes into itself one time. Any number divided by 1 is itself. So if you have, say, an order for 50 mLs an hour or 25 mLs per hour, whatever your hourly rate is going to be your drops per minute. So 50 mLs an hour becomes 50 drops per minute using the division factor. Now with your macro drip tubing, these are the tubes, this is the tubing that delivers larger drops. If you have tubing with a drop factor of 20 drops per ml, you're going to divide the hourly rate by 3. 20 times 3 is 60. And when I set this up in dimensional analysis, you'll see how it kind of makes sense. But anyway, if you have a rate that's 120 mLs per hour, you divide by 3 to get 40 drops per minute. And that's the division factor for for a tubing with 20 drops per ml. If your tubing has 15 drops per ml, you're going to divide the hourly rate by 4. 15 times 4 is 60. So using that same order, 120 mLs per hour, you get 30 drops per minute. If your tubing has 10 drops per ml, divide the rate by 6. 10 goes into 60 6 times. So that same order for 120 mLs per hour is now 20 drops per minute. It always works. And let me just kind of show it to you so that it makes sense. Okay, so using the division factor is real simple and intuitive for some people, and for others they say, I don't understand it, it's confusing. So I'm going to try and explain it in dimensional analysis. If it still doesn't make sense to you, then don't use it. Just use the dimensional analysis that you already know how to do. But the division factor is a quick, easy way you can look at a problem and see it. As long as your computation is correct, it will work. And I'm going to explain how it works to you. Okay, it helps if you know how to reduce fractions by finding common factors. But anyway, when you set up any IV gravity tubing from an order that's specified in mLs per hour, you'll get this. You'll get this basic formula, okay? You're going to have your drops per minute as your answer. So your tubing drop factor goes on top. Your 60 minutes is always going to go on bottom for your minutes. Everything else is going to cancel out. So you're always going to end up with this same basic formula. Now, if you know that every tubing has a drop factor that's divisible by 60, and you know how to you know how to simplify a fraction, okay? So 20 over 60, to simplify that, if we had 20, you find the greatest common factor, which is 3, and you divide. So 20 over 60 is the same as 1 over 3. Okay? I'll erase it, just so you can kind of beat a dead horse. It's fine, I don't mind. If your drop factor is 15, 15 over 60, 1 over 4. Okay? And the same thing happens when you use a drop factor of 10. 10 over 60, when you simplify that fraction, you end up with 1 over 6. Okay? And then what you're left with is really your hourly rate divided by that number, by the division factor. Okay? So that's how it works. Here's an example down in blue. Okay? I was going to erase all my mess, but it'll take longer, so I'll just explain it. So, okay, so here in this problem, you have your drops per minute as your answer. Your drop factor is 20 drops over 1 ml. Your hourly rate is 120 mLs per hour. Hours cancels, mLs cancels. You're left with 120 times 20 over 60. 20 over 60 can be reduced to 1 over 3. So now you're left with 120 over 3, which equals 40. That's how it works. Do you have to do all this fancy math? No, just know that that formula, that division factor, is something you can trust. That if you have a 20 drop set, divide by 3. If you have a 15 drop set, divide by 4. If you have a 10 drop set, divide by 6. Micro drip tubing, leave it alone. Hourly rate equals drops per minute. Okay? So if that helps you, great. If not, use dimensional analysis. But either way, it's really not as hard as it seems. The harder part is actually standing at the chamber with your watch, trying to get it all perfect. And then your patient lifts their hands or you raise the bed and the rate changes because it's gravity and that's physics. Anyhow, good luck with skills testing and with your senior year. Bye.